This is question 3 of the Regression Models book, chapter on generalized linear models. The question asks true or false that generalized linear model assumes an exponential family for the outcome. Of course, you can just read the chapter and see that, of course, this is true. However, the question asks us to discuss, and that's what I'd like to talk about in this video. So I want to remind us that our data is coming of the form we get a y, so we get a bunch of values of y, and we get, say, an x, maybe an x1 and an x2. We get a bunch of values for those. Okay? So we need a model that connects our y with the x1 and the x2. The linear model does that in a sense very directly by equating them even. It equates them with a straightforward equation, and because this relationship won't, of course, naturally hold, it adds an error term, assuming that the error term then is probably normal, or at least making a first and second moment assumption about the error term. A generalized linear model does not form such an equation. In contrast, it starts. So in that model formulation, we started out with an equation that we wish was true, and then added the statistical assumptions with the error component. With our generalized linear model, we're going to start with assuming a distribution for the y. That y, we're going to assume, comes from an exponential family distribution. An exponential family includes the normal, so linear models are a special case of generalized linear models. It includes the Bernoulli and binomial distributions, the Poisson distribution, the gamma. Okay, so it's a very rich family of distributions, so it's a large collection of models that we can build. And then we still, even though we've at this point only assumed a distribution for the y, we need a way to relate the y to the x1 and the x2. This is done by the fact that the exponential family is always parameterized by a couple of parameters, in the same way that the normal distribution is parameterized by a mean and the variance. The binomial distribution is defined by a number of trials and the success probability, and the Poisson distribution is parameterized by a mean. All of these distributions depend on a parameter. One of the most important parameters that they always depend on is the mean. So let's call the expected value of y, or mu, is one of these important parameters that the exponential family depends on. So the way we connect our y to the x's is through this exponential family, through its parameter mu. This mu is now going to be connected to our x1 and x2 by the link function. Let's say the link function is g. We're going to assume that g of our mean, say, is beta naught plus beta 1 x1 plus beta 2 x2. And that might seem like a very circuitous way to connect y's and x's when in our linear model we do it with inequality. It's a very powerful way of doing things. And the reason, there's many reasons that we talked about in our lectures, but they include things like the ability to continue modeling the y on its natural scale, okay? Elegantly handling constraints, such as the fact that the y and hence its mean may have to be strictly larger than 0, or a count, or in the Bernoulli case can only take on two values of 0, 1. It handles all these cases in one elegant framework. Just to give you one simple example, in Poisson regression, mu is the parameter for the Poisson, and we're going to assume g is the natural log function. So the natural log of our mean is the linear predictor, beta naught plus beta 1 x1 plus beta 2 x2, in this case where we have two regressors. Okay, so that's what generalized linear models are accomplishing. We connect our y to a distribution that's an exponential family. That exponential family is parameterized by the mean. That mean is then connected to the regressors through the link function